We've been talking about bearings, rolling, sliding, hydrodynamic, hydrostatic. All of those, with the exception of flexural and magnetic, rely on proper lubrication. How the load is applied will affect the type of lubrication you want to use, and both of these together then will affect the life of the bearing. The study of lubrication is called tribology, and it's very, very important that the materials of the bearing, the actual lubricant, the type of loads and operating environment, and the surface finish of the bearing elements be considered. The nice thing is when you buy a modular bearing off the shelf, you will typically be specifying the types of load and operating conditions, and the manufacturer will then recommend and supply the bearing with the lubrication you need already loaded. And your best world is if you can have a greased for life bearing with seals such that you never actually have to ever lube it again for the intended operating life of the machine. For a very long range of motion of machines, long lifetime, you will have to be considering the design of the lubrication system for your machine. That may be as simple as there being little grease fittings in your machine, like here, and then a maintenance procedure for once a year, grease your fittings with 2 shots, which correspond to so many grams of such and such type lube. In a machine that may have dozens of these carriages, getting to dozens of them to lubricate them would be pretty bad. That's where you need to start designing tubes between them all so that you can have one point of lubrication or a central lubricator system. System design being the key operative word. When you're buying bearings off the shelf, you're not going to have to be worrying about surface finish per se. If you're designing the bearing system from scratch using modular, for example, sliding element bearings on rails that you purchase or have made yourself, this is where you start to worry about how you've achieved the surface finish you require. Sliding contact bearings in particular are very, very sensitive to the lubrication you apply because they often rely on the hydrodynamic wedge to be built up. Or if they're moving very slowly, so you have what's called a boundary layer or mechanical sliding contact, the surface finish is very important such that you don't have little sharp spikes or what are called positive skewness, which act like little file teeth. You want to have little valleys that will hold the lubricant, such as this one structure moves on top of the other, it'll slowly draw out a little bit of lube and help it slide better with less wear. We had alluded to this earlier of doing the calculations for the PV value of the bearing. That's the applied pressure times the velocity, which has to be below a maximum. And indeed, you can calculate based on the type of bearing material how much wear you get. In other words, for every kilometer of motion of the bearing at this PV value, expect there to be so many microns of wear in the bearing. That's information that the bearing manufacturer should provide for their material. Again, you can write a spreadsheet to predict and see what's happening with it. For rolling contact bearings, the type of contact surface, for example, is it a circular arch bearing or a Gothic arch bearing, this configuration being used in single rolling element rotary bearings that can hold a moment load without having to have 2 bearings together to resist that moment load, will affect the type of lubricant also. The nice thing is that the ball bearing manufacturers are very good about recommending the type of lubricant to use and how much to use for your application. The lifetime of a ball bearing, be it a rotary motion, linear motion, ball, or roller, is calculated with this type of equation, typically called the L10 life for the rotary motion bearing. That says this is the number of revolutions you'll get when 10% of the bearings fail. And they're all based on, for ball bearings, some dynamic load divided by the applied load to the third power. So the CO is the dynamic load capacity of the bearing. That comes from the catalog. So in other words, life at which 10% of the bearings fail after 1 million rotations, right? It's proportional to the dynamic load capacity of the bearing divided by the load applied to the third power. And this is for a ball bearing. It's to the 10-third power for a roller. For a linear motion bearing, you typically have what's called the L100 life. And that means I can get 100 kilometers of travel. Same factor of 3 and 10-thirds for balls versus rollers. Now, a lot of the linear motion bearings, particularly in the automation, high-speed automation machines, will put 1,000 kilometers on the machine in a year. They run 24 hours a day, 7 days a week. For those high-speed applications, very, very long life, you have to work with the manufacturer's catalog for the, and there's some coefficients on these equations, on how to predict the life of that bearing. On those types of very high speed, very, very long travel motions, it becomes even more critical, the mounting of the bearings, such that those parasitic forces caused by misalignment acting through the stiffness of the bearing to create that misalignment force can be the dominant load and life limiter. The lubrication then for these very high speed, very long life bearings is even more critical, because over the years the lubricant can slowly ooze out or oxidize and be damaged, and how you design in either a wick type system to constantly bathe it in a little bit of fresh lubricant every time, or a center lubricated system is critical. For clean room applications where you can't have lube dripping out, these types of bearings also come with seals and or special retaining features in that hold the rolling elements and separate them with little lubrication pockets, where you have just enough lube to help the bearing roll, but it doesn't drip out. Why do we have to grease a rolling element bearing? I thought that was the beauty, that it rolls. Why does it need lube? Well, remember the Hertz contact, the rolling element, and the rolling element is not round under load. So where is it? That the radius of rolling? What is this radius here as the thing is mushed? For rolling contact linear bearings on these high-speed motions, as we had discussed earlier, the alignment is critical for the loads because that's the F equals Kx function. The lubrication is often achieved with either the Zerk fittings independently, one bearing at a time, or they're all linked together. And a very important virtual effect of lubrication is if I have a linear motion axis, another linear motion axis on top, and I'm moving one through a sine wave and one through a cosine wave, such that together I trace out a circular pattern. For example, a milling cutter is coming down, milling out a circle. A subtle yet very important factor is when I'm rolling, I'm rolling, and then I stop, and then roll to go back, because This is my x-axis and my y-axis. In order to make this part here go in a circle, it's going down and up, down and up. This reversal point causes the rollers, when they're moving this way, boom, stop and then go back. There is a little bit of hysteresis that happens upon that reversal cycle. And you can imagine that here is the roller that's smashed between the rails, the raceways. And I've drawn it purposely a little bit of oblong because as I'm shearing it this way, I get a little bit of deformation in it. And when I stop and back up, I get a parasitic air motion. And indeed, if you look at the circular trace, you think you're tracing on a perfect circle, but at the poles, there are tiny little bumps. These bumps may only be a micron or a fraction of a micron, that is a millionth of a meter or less. You may never notice them. If you're doing a wafer stepper or a very, very high precision grinding machine, chances are you will. The lubricant that is used, and indeed the preload that is applied, will have a profound effect on this reversal hysteresis. How do you predict it? Very, very difficult. But you can measure bearings, get the data from the measurement, and build that into your database of understanding as to what the amount of preload, what type of lubricant can you use to minimize this effect. These subtle types of effects are the difference between machines that can dominate the planet with happiness and performance, and those machines which look really creative but really don't work so well. How about flexures? Well, there's no lube, but load and life are very important, and it's actually fairly easily calculated simply because the flexural element doesn't have the unknowns of wear associated with did I get the lubrication right or the surface finish right. So the life of a flexure is fairly easy to predict based on understanding of solid mechanics, and just it's a fatigue life calculation. Seals. Now ideally, intelligent design would prevail here, which is why fish don't have propellers, because God knew there'd be a problem with the seals. The best bearings use no seals. But most bearings need seals simply because you'll have a lubricant to protect the rolling elements, keeping them rolling smoothly, minimize friction, and the seal protects the entire system from dirt getting in there, which could grind up and really cause a high failure. The problem with a seal is if it makes mechanical contact, it's a sliding contact and it generates heat. So it can actually burn up. And many a high-speed spindle has failed because the seal was misapplied, too much force between the seal and the body it was touching, and you just had too much heat, which causes runaway failures. So as odd as it sounds, even though the seal doesn't carry any load, it's not a high stiffness, it's just there to keep things clean, is often the most critical element on your machine. Systems, bearings and systems. How do we align things properly so they're always not only really good looking, but perform just really nice? All these machine elements and everything we've talked about in the last 10 lectures all leads us to understanding of individual little pieces of the machine, and indeed how some of these pieces interact with each other. For example, how the actuator through the center of stiffness keeps the bearing moving without tilt. What we're going to be doing next in topic 11 is looking at how do we predict the performance of the entire machine at a large assembly of bearings, actuators in the entire structure. And indeed, the interaction of all the elements through the structural loop and the changing shape of the machine and of that structural loop made possible by the bearings is going to be your key to being able to create machines to do fantastic things.